In this video, I'm going to teach you how to use MATLAB to calculate the inverse Laplace transform of the output. First, let me introduce you some MATLAB commands, how to manipulate polynomials. To define a polynomial, we can use the coefficient in the polynomial by defining a vector. For example, for the polynomial s cubed plus 3 times s squared plus 4. So the leading coefficient is 1. Then we have 3. Since there is no s, so it is 0. And the constant term is 4. Let me run this step by step. So P is a vector. The roots is a MATLAB command to calculate the roots of the polynomial. So for this polynomial PS, it has a real root and a pair of complex roots. Then the MATLAB command poly is to construct a polynomial based on the roots. So R is the roots calculated from this polynomial. So let's construct another polynomial using the roots. Now you see the polynomial P and polynomial P1, they are the same because they have the same roots. So the coefficients are the same, 1, 3, 0, and 4. Next, let's discuss the multiplication of polynomials. Let's see here we have two polynomials multiplied together. So to define the first polynomial, its coefficients are 3, 2, and 1. The second polynomial is 1 and 4. Then we use command convolution. So here in MATLAB, convolution means two polynomials, the multiplication of two polynomials. So n returns the coefficients. Then now we have the result of the multiplication of two polynomials. So it will be 3 s cubed it will be 3 s cubed plus 14 s squared plus 9 times s plus 4. We can also evaluate the polynomial at a particular value of s. So let's evaluate the polynomial at s is minus 5. So we use poly val. Then the polynomial is n, s is minus 5. Then we get the value is minus 66. Since we know the first step to find the time response of a control system is to calculate the Laplace transform of the input signal. So let's see this example. Suppose the input signal is 1 plus 2 times sine Wt. First, let's define symbols. We use the MATLAB symbolic toolbox. We define the symbols S, T, the time, and W is a constant. Then we use Laplace. 1 plus 2 sine Wt. And here it shows the Laplace transform for this time signal. Let's see another example. The input signal is A times sine Wt. Again, let's define symbols S, T, W, and A. Then we use Laplace. Then you see here the result is the same, except the A is replaced by 2, or 2 is replaced by A. For the constant term, 1, its Laplace transform is 1 over S. Let's see another example. We have the input signal, the time t times sine Wt. Again, let's define symbols S, T, and W. Then we use Laplace transform. So in this case, the Laplace transform is 2s w s squared plus w squared then square. MATLAB can also help you to do the partial fraction expansion. First, let's consider the case. So all the roots are different but real. This is the example I think you did in the class. We have ys. The numerator is s plus 2 times s plus 4. The denominator is s times s plus 1 times s plus 3. Then to form the numerator polynomial, we can use the convolution, 2 polynomials times together. So here the coefficients are 1 and 2. So second is 1 and 4. Then for the denominator, since the convolution can only work for multiplication of 2 polynomials, then let's multiply the first 2 polynomials. So it will be s squared plus s. So the coefficients is 1, 1, 0. For second polynomial, it's 1 and 3. Then we can use the MATLAB command residue. The numerator and denominator to find the partial fraction expansion. First, let's run this command, then I will explain to you what RPK means. Here we have the result for the partial fraction expansion. So R would be the coefficient, so P will be the roots in the denominator. We have minus 3, minus 1, and 0. Then for S plus 3, so the coefficient is minus 0.1667. Then for the root, minus 1, s minus 1, s plus 1. The coefficient is minus 1.5. Then for the 0, its S coefficient is 2.6667. Then what's K here? So K, usually in control system, so K is empty. So K only appears when the order of the numerator is greater than the order of the denominator. Then we have some polynomials for the K. For example, the K, when the order of the numerator is greater than the order of the denominator, maybe we have some terms, let's say S plus 1. So in this case, the K is not empty. But for control system, the order of the denominator is greater than the order or equal than the order of the numerator. So in general, the K is empty. Now let's see another example. We have the numerator is 2. We have 3 roots. So it's -1, -2, and -4. So the numerator is 2. So the denominator, we can use the roots to form the polynomial. To have roots -1, -2, -4, we use poly. The command here, poly, to form the polynomial. Then we can calculate the residue. That's the partial fraction expansion. So here it shows the result. So we have for S plus 4, it's the -4. S plus 4, the coefficient is 0.3333. Then for S plus 2, we have -1. Then for S plus 1, we have 0.6667. Now let's discuss a case we did not discuss in the class. That's the case we have real roots, but they're repeated and not distinct. They're repeated real roots. So let's see this transfer function. The numerator is 2. Then it has 3 roots. It's -1 and -2 and -2. So the roots -2 are repeated, but we can still use the command residue to find the partial fraction expansion. Then how to interpret this? Let me show you. So for the 2 -2, so one of them is S plus 2, then the other one will be S plus 2 square. This is a different part from the real roots, but distinct. When there are repeated real roots, so one of them is S plus 2, so the other one needs to be S plus 2 squared. So the coefficient for them is -2. -2 and -2. Then for S plus 1, coefficient is 2. So that is the partial fraction expansion. So you can also use a command inverse Laplace to calculate a time function. So here it is another example. We have the numerator is s plus 3. So denominator is the same like here, s plus 1, s plus 2 squared. We have repeated real roots. But in this case, you see we have again repeated roots for -2 to have s plus 2 plus s plus 2 square. Then this is a different part from the real roots, but distinct. So the coefficient are -2, -1. Then for s plus 1, the coefficient is 2. Yeah, we can use the inverse Laplace transform for inverse Laplace transform for this transfer function, or the output of the Laplace transform of the output. Let's see, let's define symbols s and t. We use inverse Laplace. So that is the time function. It is 2 exponential minus t minus 2 exponential minus 2t minus t exponential minus 2 times t. So let's compare. So from the partial fraction expansion, we have s plus 2 plus s plus 2 squared. Then the coefficients are -2, -1, then plus s plus 1, the coefficient is 2. So if we apply the inverse Laplace transform, have this term here, 2 exponential minus t. Then we have here, for the second term, -2 exponential minus 2t. So the last term is -1. So it's exponential minus 2t, but times t. Now let's see the case of partial fraction expansion for distinct complex roots. Let's assume this is the output, the Laplace transform of the output. The denominator is 3. Then the numerator is s cubed plus 2s squared plus 5s then we can define the numerator and denominator. Then we can apply residue. If you see, it has the polynomial, the denominator polynomial. It has one real root and a pair of complex roots. Here, one real root and a pair of complex roots. Then this is the coefficient. Similar way, you should have some terms like this. So for this one, we have s plus 1 minus 2i, 2j. And the coefficient is minus 0.3 plus 0.15 j, then plus s plus 1, then plus 2j, and the coefficient minus 0.3 minus is here 0.15j. Then we have the s coefficient 0.6. We can also directly calculate the time function using the inverse Laplace transform. S cubed plus 2s squared plus 5s. So that's a time function. 3 over 5 exponential minus t cosine 2t plus half sine 2t. I think we did this example in the lecture. Here is another example. For distinct complex roots, the numerator is 1, the denominator is s cubed plus s squared plus s plus 0. So it can be considered as the multiplication of two polynomials. So for the first polynomial, the coefficient is 1, 0. For the second polynomial, it's 1, 1, 1. Then we can apply residue to calculate the partial fraction expansion. So here it shows the result. And for the first one, we have s plus 0.5 minus 0.866j. And here the coefficient minus 0.5 plus 0.82887j. And for the second term, we have s plus 0.5, then plus 0.866j. The coefficient 0.5 minus 0.2887j. And for the last term, is s is 1. In MATLAB, we can directly calculate the inverse Laplace transform from the Laplace transform of the output. For less, define symbols S, T, and A. We use inverse Laplace transform to 1 over S cubed minus A S squared. And here we obtain the time function, the exponential AT over A squared minus T over A minus 1 over A squared. Another example, apply inverse Laplace transform to 1 over S times S plus 2. The time function is 1 over 2 minus exponential minus 2 times T over 2. The last example, apply the inverse Laplace transform to 1 over S times S squared plus S plus 1. That will be this case. We have a pair of complex roots. So time function is 1 minus exponential minus T over 2. Then have cosine square root 3 T over 2 plus square root 3 sine square root 3 T over 2, then over 3.